Look at a typical street on a sunny day. A dog running on a porch, a bicycle zooming past, a truck rolling by. For us, making sense of this chaos is automatic. But for a machine, this is just a grid of colored pixels. Yet, as you can see in this image, an algorithm can drop precise colored bounding boxes around the dog, the bicycle, and the truck, cleanly isolating them from the background. This exact same capability scales up to entire environments. Here, an array of satellite imagery shows how a machine categorizes vast landscapes, instantly sorting diverse aerial textures into airports, forests, and rivers. If you try to write traditional code to do this, you fail. It is mathematically impossible for a programmer to write a manual set of rules defining the exact pixel arrangement of a dog's fur or the precise geometry of a forest canopy from space. The breakthrough required abandoning those rules. This diagram maps how the machine learns using a three-part mechanism. It takes in training data, uses a loss function metric to calculate the error, and relies on a feedback loop to update its own parameters. Engineers stopped trying to program intelligence directly. Instead, they built an engine that autonomously learns its own boundaries by constantly measuring its own failures. To make sense of an image, the system cannot look at the raw pixels all at once. It has to extract abstract elements, called features, like simple edges, textures, or color gradients. In a deep neural network, raw pixels flow into layers of artificial neurons, gradually transforming into geometric lines and shapes. These edges converge into a single circular node, where incoming signals are multiplied by weights, shifted by a bias, and combined into one numerical output. Because those weights start out as completely random numbers, the network's first attempt at identifying the image is a completely blind guess. That first prediction is almost always wrong. This is where the metric comes in. A mathematical formula called a loss function precisely calculates the distance between the machine's incorrect guess and the actual correct answer. This initial ignorance is intentional. The network has to fail, and we have to measure the exact size and direction of that failure, because that error provides the exact coordinates needed for the machine to learn. Once the error is quantified, a feedback mechanism kicks in. The system transmits that calculated loss backward through the entire network to trigger adjustments. We can visualize this correction process as a spatial problem. This graph shows an algorithm trying to separate two data classes. Using a learning rate, it incrementally tweaks its weights and bias, physically shifting its mathematical boundary closer to fixing the misclassification. This rapid, continuous cycle of looking at the data, making a guess, measuring the error, and adjusting the weights is called an epoch. Scale this up across a deep network, and you get thousands of micro-corrections looping continuously. A rigid, incorrect boundary line rapidly shifts and bends across the entire dataset, eventually settling into a curve that perfectly separates the variables. The black box of AI operates entirely on this relentless cycle. It simply makes millions of mistakes and applies microscopic mathematical tweaks until it becomes incrementally less wrong. You might assume that if the network runs enough epochs and drives its training error down to zero, it has successfully learned. But a low error rate does not actually mean the machine has become intelligent. This side highlights overfitting. Memorizing exact training data minimizes training error, but generalization error stays high. It will fail to recognize new real-world objects. On the opposite end is underfitting, where the model's parameters are simply too rigid to capture the necessary pattern at all. The solution relies on Occam's razor. Looking at these three graphs, the goal isn't the underfit straight line, nor the wildly zigzagging overfit line that bends to hit every dot. The ideal learning model finds the smooth, elegant curve in the middle. The ability to seamlessly identify objects in the chaos of the physical world is the result of millions of automated, scaled corrections, perfectly balanced to extract the simplest mathematical truth hidden inside the noise.